Hello everyone, welcome to my DataCamp tutorial series. I'm Professor Adam Kroom, and today we will focus on AI Fundamentals Chapter 4, Deep Learning and Beyond. Go ahead and hit Continue Chapter, and it will take you to the first video called Deep Learning and Beyond. Watch the video, it'll give you important information on how to solve the exercises in the chapter. After you've watched the video, hit Next Exercise, and it'll take you to this exercise called the nucleus. Artificial neural networks are built from artificial neurons. Just like human neurons, artificial neurons have input pathways, bringing the signals to the neuron, and output pathways, leading the resulting signal further. The values of the input signals have been aggregated, usually just summed up. Then the final output value of the neuron is defined by a function. What is this function called? And we have three possible answers. The first is the transfer function, the second is the activation function, and the third is the input function. And I'm going to pick activation function and submit answer. That's correct. The activation function is usually a nonlinear function like a sigmoid or a rectified linear function. Press enter to continue. The next exercise is called How to Train Your Dragon. For a long time, neural networks were more of a theoretical concept than a practical tool. The reason for this was the lack of an efficient training algorithm. This all changed in 1986 when a group of authors published a famous paper. Which revolutionary algorithm did this paper further improve and popularize? We have three possible answers: the moonwalk algorithm, backpropagation algorithm, or back to the future algorithm. And I'm going to go ahead and pick backpropagation. Yes, the backpropagation algorithm gave a huge boost to the field of AI by radically improving the efficiency with which neural network models were trained. Press enter to continue. The next exercise is called Your First Neural Net. All that buzz around AI and deep learning, but we already promised you it is not so scary when you take a look under the hood. You're going to create your first neural network to solve a classification task. You are working with labeled sensor data, which has 16 input columns representing 16 features coming from a movement sensor of a smartwatch, and a target column representing one of four movement types: walking, running, sitting, or lying. All the ingredients have been loaded for you, the sequential model and the dense layer. You just have to put the ingredients in the right order, just like stacking pancakes. Instructions: initialize a sequential network. Set a fully connected dense hidden layer with 8 units, neurons, making sure to specify the correct input size to match the dimensions of the input data. Set another fully connected dense layer at the output, making sure to specify the correct number of output units, defined by the number of output classes of your problem. Compile the model. All right, so looking over on the right, it says initialize the model. So model equal to sequential, right? It says right here, initialize a sequential network. So I just type sequential right there. Next, it says add the hidden and the output layer, specify the layer type, number of units, and input output dimensions. Okay, so it says model.add, and then we know from our instructions, it says set a fully connected dense hidden layer. So right here, we're gonna type dense. Units equals 2. Well, it just told us hidden layers with 8 units. So units equals to 8. Input underscore dim equals 2. We set that to 16. And activation equals 2. That's already filled out for us. Next, it says model. The next blank spot to fill in is right here, model dot. And that's model dot add. And just like above, dense, units equals 2, this time equals to 4. And compile the model. No problem. So for this, it says model dot, and then we have to fill in a blank. That blank is compile. Yeah, to compile the model. And let's submit that answer. Well done. How about that? Already making your first neural networks, are you? Press enter to continue. We're at the next video called Deep Learning. Go ahead and watch this video. It'll give you information on how to solve the next exercises in the chapter. After you watch the video, hit next exercise, and it'll take you to this right here called layers. There are many types of layers in deep learning. One type in particular could be signaled out and given credit for their rise in power and popularity, enabling neural nets to become champions of image classification benchmarks. Which one is it? And we have 4 possible answers: convolutional layer, dropout layer, max pooling layer, and flattening layer. And the correct answer is convolutional layer. Yes, convolutional layers, which are at the core of the convolutional neural networks, were one of the biggest game changers in the evolution of neural network algorithms. Press enter to continue. The next exercise is called Guess the Architecture. Steamify, a new audio streaming platform, entered the market. From day one, they are running into an issue. With hundreds of new artists and songs uploaded daily, there is rarely enough time to appropriately classify the content into genres, which significantly hurts their users' experience. Streamify wants you to train a deep learning model to perform this task automatically. You take up the challenge. Since you're dealing with a gigantic amount of audio data, whose main dimension is time, which of the following networks is the perfect candidate to extract patterns? We have possible answers: convolutional neural network, recurrent neural network, and feed forward neural network. And the correct answer is recurrent neural network. Exactly. Whenever you need to understand patterns in time, recurrent neural networks are the first logical choice. Press enter to continue. The next exercise is called Rolling in the Deep. You have already been asked by the local police department to produce a deep learning model for license plate reading. Your input data are images of digits, 28 pixels wide and 28 pixels tall, each with a label stating which of the 10 possible digits is present on the picture. The sequential model is already loaded, which you will use to build a deep neural network using the following layers: conv 2D, 2D convolutional layer, max pooling 2D, pooling layer, flattening layer, and dense, fully connected layer. Our instructions are the following. Initialize the model and set a 2D convolutional layer with 64 filters of size 3 by 3 at the input. Add a max pooling 2D layer with default parameters, followed by a flattening layer to reshape the signal from a 2-dimensional to a 1-dimensional format. Add a fully connected dense layer with a softmax activation function and 10 neurons for 10 target classes present in our training set, and compile the model. So looking over on the right, it says initialize the model, and that's been provided for us. Next, it says create your 5-layer network, input specified implicitly with first layer. Okay, so model.add first conv to d. Yeah, this from right here over on the left, conv to d. Filters 64, and kernel size equals 2, 3, 3, and input underscore shape equals 2. 28, 28. And next, on line 6, model.add. And this time, instead of conv 2D, we're using this one, max pooling 2D. Yeah, so I'll just go ahead and copy from the left and paste it over on the right. And then next is flatten. So go ahead and copy flatten and paste it over here. And then finally is dense. So I'm going to copy dense from the left and paste it over here on the right. Units equals 2, 10. And then finally, it says set fitting hyperparameters and compile the model. And we know how to compile the model, model.compile. And submit answer. Great job. So you see, when you know exactly what you need to do, you can construct a very powerful deep neural network in less than 10 lines of code. That's how far the ecosystem of AI frameworks has gone, and the progress is not slowing down. Press enter to continue. We're at our next video called Convolutional Neural Networks. Watch the video, which will provide you with information on how to solve the next exercises. After you've watched the video, hit next exercise, which will take you to this exercise called The Beauty of the Beast. Convolutional neural networks have come to dominate the domain of computer vision. What is the key reason and fundamental difference compared to traditional computer vision algorithms? Why this is the case? And we have 3 possible answers. CNNs autonomously learn optimal feature transformations, leading to best possible performance. CNNs convert low resolution images to high resolution ones, or CNNs learn from a small amount of data. And out of those 3, I'm going to go with the first one. Exactly. Press enter to continue. Our next exercise is called one-liner modeling. Modern deep learning libraries already help you by abstracting an ever bigger part of work that was once required to build neural networks. As you could already see, in just 10 lines of code, you can specify an extremely powerful network that could be trained for days using terabytes of data. But sometimes you want to go even further in abstraction. When you have a typical network specification that you often use, changing only a handful of parameters, it's a good idea to enclose it in a function. That's what you will do in this exercise, and later reuse the created function for further exercises. Our instructions are the following. Specify the default number of kernels as 32. Specify the default kernel size as 3, fix the optimizer type as atom, and set accuracy as the optimization metric. So looking over here on the right, we have to set n underscore kernels equals 2. It tells us right here, 32. So I'll type 32, and then kernel underscore size equals 2. Excuse me. 3. And we get that right from right there. And next, all of this has been filled out for us. Very nice. And then what we have to do next is compile the model. So we have model.compile optimizer equals 2. And it says right here, set it as atom. What a great name, atom. And then metrics equals 2. And then it tells us right here, right? After fixed optimizer type is atom, next is set accuracy. So in here for metrics equals 2, we're going to type accuracy. Loss equals categorical underscore cross entropy, return model, and submit answer. Good job defining the make underscore deep underscore net function. It's going to make it easier to build larger networks in the coming exercises. Press enter to continue. The next exercise is called one line evaluation. Although constant progress is being made, not all outputs of your modeling and evaluation algorithms come in a human readable shape. Very often, they come in plain arrays of unnamed values, requiring you to read through the documentation in order to interpret what each value means. In such cases, it is again clever to make wrapper functions that format and return the results in a neat and understandable way. The evaluation result, stored in the variable score, is an array whose first element is the loss and the second accuracy of the model over the given dataset. The instructions are the following. Place the input variables x underscore test and y underscore test into the appropriate arguments of the model's dot evaluate method, and use the first element of the score array to print out the loss and the second element to print out the resulting accuracy. Looking over on the right, it says generate the test predictions and evaluate against the ground truth. So it says model.evaluate x equals to, right here, we'll take x underscore test, copy, and I'll paste it right there. And then y equals 2, and I'll just copy it from over here, y underscore test, and I'll paste it right over here. Next, print the evaluation results in a human readable form. So we have percent score. In there, we'll just type 0. And 100 score is 1. And submit answer. That's it. Making convenient wrapper functions for humanizing the outputs of your model is a very good practice that will make your work with building and evaluating machine learning models much more pleasurable. Press enter to continue. The next exercise is called deep learning for digit recognition. Deep learning models excel at classifying unstructured data, such as images and text. Common problems solved by deep learning include image classification, object detection, text translation, and text summarization. In this exercise, you will use the functions defined in previous exercises, make underscore deep underscore net and evaluate underscore deep underscore net, to build a deep neural network for recognizing handwritten digits. You will train and test your model using the well-known MNIST dataset, which contains a collection of images of individual handwritten digits, each 28 by 28 pixels big. The dataset is preloaded and split into the training and test sets provided right here. Instructions, we have 4 parts. The first one says construct the neural network, taking into consideration the input data, dimensions, and the number of output classes. Looking over on the right, it says construct the deep neural network. So, let's see. Well, we know that the digits are 28 by 28, so we'll fill in right here, 28 and 28. And n output classes equals to 10. And let's go ahead and submit answer. All right, so part 2, call the fitting function of the model. Set the model training and validation data and use batch underscore size equal to 128 and only one training epoch during the fitting. Okay, so looking over on the right, it says train the deep neural network. So we're going to use deep underscore net dot fit. So type in fit right there. X equals to X underscore train. Y equals to type Y underscore train. And then validation underscore data equals to x underscore test. And next, y underscore test. For batch underscore size equals, set size equals to 128. And then epoch, set that to 1. 1 training. And submit the answer. All right. Now we're on part 3 of 4. So we still have 2 more parts to this exercise. This part says evaluate the trained model's performance. Okay, so on the right, it says estimate the network performance. We have evaluate underscore deep underscore net. First argument, we're going to type deep underscore net. Next, x equals 2, in that blank spot, type x underscore test. And then finally, in the last blank spot, y equals 2, type y underscore test. And submit answer. Cool, we're on part 404 of the instructions, which tell us to compare the change in model performance if you go from 1 to 3 training epochs. All right, so before we just did 1, and now it wants us to do 3 instead. So let's go ahead and do that. Right here in the blank spot, we'll just type in 3 and submit. As expected, starting from 1 and then gradually increasing the number of training epochs normally leads to better performance, but only up to a certain threshold. You must also keep in mind that training real-life models takes a lot of computing time and power. So you're looking for the number of training epoch that is just good enough, not perfect. Press enter to continue. Congratulations. I believe that completes chapter 4 of AI fundamentals, deep learning, and beyond. And this is also the last chapter of the course overall, AI fundamentals. So thank you for your attention. I hope you found the tutorial useful. I'll go ahead and post a distinct set of tutorials for the next course.